Now we're moving on to the next unit, which is unit 6, and we're going to start looking at these things called quadratics. So in the first part of the um, lesson, we're looking at patterns. So we're going to be looking at these three tables, and we're going to see if there's a pattern that exists here. So notice here that as x increases, so x goes 1, 2, 3, 4, 5, y also increases, and you'll notice that it also increases by the same number. So it increases by 5, then it increases by 10, then it increases by 15, then it increases by 20, and so on. And so this is kind of a linear relationship because both are increasing and we have some type of pattern that's really being followed in this particular case. If we were looking at the equation, we could figure out what this pattern is doing in this particular case and be able to identify it and see what's going on. So um, that's the linear type of relationship. We notice on this one, same kind of thing, 1, 2, 3, 4, 5, and we can see that x increases and does have a pattern. Notice here, 3 times 2, 6 times 2, 12 times 2, 24 times 2, and it keeps increasing. And that's going to be linear too because we're just basically multiplying it by 2 each time. So we're not really doing anything else but multiplying it by 2. So we can kind of get a good idea as to what's happening with that and be able to figure out what that pattern kind of looks like. On this one, 1, 2, 3, 4, 5, but you'll notice that the y value goes up, then it starts falling, and there really is no pattern to it. It goes up by 3, then it goes down by 1, then it goes down by 5, then it goes down by 9. So it's actually kind of a weird way of doing it, but we can't specifically identify a pattern that we can see in those particular numbers. So that's what we're looking for. And the one that we're going to start looking at is we're going to start looking at equations that you can't really recognize the pattern as easily as you can in these first two. So we have a garden that we're building, and Noah wants to build this garden. And I thought I drew it. So we have a rectangle. We have our width and our length that are identified in our rectangle. So it says label the length and the width of each one. You notice that we have a total of 50 meters of fencing. So that's our total that we're going to be working with. So that means that the entire fence starting right here, from here to here, back down and back over, that's going to be 50 meters. So based on that information, we know that going from here all the way up to here has to be half of that because we have our width, our length, our width, and our length. And so half of it goes from here to here to here. So that would be 25 meters of fencing. So if we're going around just to there, that's 25 meters of fencing. That's going to be important here in a second. So find the length and width of such a rectangle that would produce the largest possible area. So what we're going to do is we need to know the length and the width. So we are going to create a table, L, W, and A for our area. And now we have to do is say, okay, we know that our length plus our width has to equal 25. We know that. And then what we need to do is we need to calculate our area, which is length times the width. So our area would be length times the width. So we need to figure out some numbers here. So let's just start picking some numbers. So for L, let's try 5. So if L is 5, then 5 plus W has to equal 25. So W has to equal 20. If I multiply these two together to get the area, I get 100. Let's pick another number. Let's try 10. So when L is 10, 10 plus what equals 25? And that would be 15. And then multiply them. 10 times 15 is 150. 150. Okay, let's continue to go. So now let's go to the next value. So notice that my area is getting larger. And we can see as we change these numbers, and then we'll kind of moving around as we go along too. So let's go up to 15. So at 15, of course, my width is going to be 10. and that's going to be 150. So that didn't change, and obviously that shouldn't have, because notice that this multiplication and this multiplication are exactly the same. So let's kind of go backwards somewhere between 10 and 15, because it seems like it's going to start going back down now, because if I were to do now 20, then this would be 5, that would be 100, so my numbers are going to start going down. So instead I'm going to pick 12. So we'll say, okay, 12 and then 12, so the width has to be 13. Remember, these two have to add up to 25. So multiply those two, I get 156. There we go, a little bit larger number. And now let's see if we can find even a larger number. So let's get kind of closer to 12 and closer to this 13 so we can do it. I'm going to actually just split them up in half. So I'm going to say half of it is going to be the length and half of it's going to be the width. So 12.5 times 12.5, and that turns out to be 156.25. And this will end up being our largest area. So notice that when the length and width are equal, we get our largest area. So that's helpful. You'll notice in the table here, 5 times 20 is 100, 10 times 15 is 150, 12 times 13, 156, 12 and a half, 12 and a half, 156.25. If I continue to go, you notice that my numbers start dropping. Okay, so this would be my maximum. So right here is my maximum value that I actually have there. So the last part is plotting. And so what we're going to do is we're going to plot those numbers. I'm going to use this one. This one looks a little nicer for the table. So we're plotting the length versus the area. So we want the length and the area is what we're plotting in this particular case. So when length is 5, area is 100. So when the length is 5, then we go up to 100 and we put a dot there. We put our dot right there. Okay, so that's our first dot. Now we go down, check again. 10, when the length is 10, it's 150. So here's 10. We go up to 150. We're going to put a dot right there. So our next dot's going to be right there. 15. If you remember 15, it was also 150. We didn't do the calculation, but at 20, it would be 100. But we still have a couple of other numbers. So at 156, at 12, it was 156. It's a little bit above the 150. And it's barely above that at 12 and a half, but it's just a little tiny bit higher. So notice that we have this shape here that looks something like this. And that shape is what is known as a parabola. So notice what happens with a shape is that it goes up. So here we go. We always go left to right. So we're walking in a sense this way. So notice that it goes up, peaks, comes back down. And there's some important pieces about this. If I were to draw a line right down the center, they went right through the maximum point right here, which is 156.25. If I draw a line right there, then what I'll notice is that it's symmetrical on both sides. Notice that both of these are at 150. Notice that both of these are at 100, and the distance away is exactly the same. So there's some properties eventually that we're going to learn about these things called parabolas, but now it's something different than the lines that we've been creating. So what do you notice about the plotted points? They create this curve. The points in this one right here, they do 3 and 66. So when it's 3, it's 66. When it's 22, it's also 66. And notice those are points that are symmetrical. They're right across from each other. So they're the same type of points. So that's what's happening with the symmetry. Could 125 represent the length? Well, let's see. So what it's saying is that here is the length and here is the area. So if the length is equal to 1, the width has to equal 24. And the area has to equal 1 times 24, which is 24. So therefore, no, this could not represent the length and area, because if the length is 1, the width has to be 24. If the width is 24 and the length is 1, multiply those two to get the area. The area is 24.